Hi everyone, welcome to week 5 of HSCI 6263. We are more than the halfway mark of what was planned for this course, and I hope that you guys are learning the basics of statistics for research, and hopefully you'll be able to apply what you're learning in real life experience very soon. This week's session is all about relationships among variables. Correlation and regression are statistical methods to examine linear relationships between two numerical variables measured on same subjects. Correlation describes relationship and regression describes both relationships and predicts an outcome. For this week, we'll be majorly looking at scatter plots, Pearson correlation, Spearman correlation, and simple linear regression. You are expected to read Chapter 8 of your textbook for this week. You'll not be tested on the final exam regarding the discussion about the sample size needed for correlation and regression. This is the discussion that was on page 214 of your textbook. But if you have time, you are recommended to read it for general knowledge. Please watch the archived videos about correlation and regression as they provide very important concepts about the two. In the next few slides, I'll provide very brief overview of the week. You have a lot to cover during the week, and I promise I'll keep this short and precise. Before moving on, I just want to remind everyone that there will be another analysis journal assignment that focuses on interpreting the results of correlation and simple linear regression. Please let me know if you have any questions as you work on your assignments. Correlation. Correlation describes the strengths of linear relationships between two variables. It's a statistical technique used to determine the degree to which two variables are related. Correlation could be presented visually or numerically. We'll be looking at both this week. For visual presentation of correlation, we use scatter plots. And the numerical way of expressing or presenting correlation would be correlation coefficients. Let's look at the visual way of presenting correlation, which are scatter plots. A scatter plot is a mathematical diagram with x and y coordinates. It visually shows the relationship between two quantitative variables. It has one variable that's called the independent variable and a second variable that's called the dependent variable. In a scatter plot, unlike line plots, the points are not joined. Here is an example of scatter plots. By visually looking at the plots, one can tell the relationship between the dependent variable and the independent variable. The pattern of the data is an indicative of the type of the relationship between the two variables. We can see that in the first plot, there is a positive relationship, meaning that as the independent variable increases, the value of the dependent variable also increases. And the second plot shows a negative relationship, meaning that as the value of the independent variable increases, the value of the dependent variable decreases. And the third plot shows that there is no relationship between the dependent variable and the independent variable. Correlation coefficient, which is also often called Pearson's correlation or product moment correlation coefficient, measures the nature and strengths between two variables of quantitative type. It's similar to scatter plots, but correlation coefficient present the relationship between the variables quantitatively. Correlation coefficients are unitless measures. The value of correlation coefficients range between -1 and +1. The sign of the correlation coefficient denotes the nature of the association, while the value of the correlation coefficient denotes the strength of the association. The closer the value of the correlation coefficient is to -1, the stronger the negative linear relationship is. This means that there is an inverse or indirect relationship between the two variables, meaning that an increase in one variable is associated with a decrease in the other. However, when the correlation coefficient is closer to 1, it shows a stronger positive linear relationship. This means that the relation is direct, or an increase in one variable is associated with an increase in the other variable, and also a decrease in one variable is associated with a decrease in the other variable. Correlation coefficients that are closer to 0 show that there is no relationship between the two variables. Correlation coefficients are usually denoted by the letter lowercase r. And correlation coefficient is calculated with the formula that's presented on the screen. Correlation coefficients can be calculated by hand. They're very simple to calculate if the data is not too big. Here is a very simple example that illustrates calculation of correlation coefficients. Let's say that we want to look at the relationship between age and weight. And let's say that we have samples from 5 individuals. As you see on the left-hand side of the table, we have the 5 individuals with their age and weights populated. So if we plug in the numbers that are required by the formula that was provided in the previous slide, one can easily calculate the correlation coefficient. The good thing is we do have statistical softwares that calculate correlation coefficients for us. In this example, I presented the correlation coefficient that I calculated manually in an Excel, and also what was calculated from the statistical software SAS. And the correlation coefficient, based on the data that we have, is 0.99, which is closer to 1. And per the interpretation guideline that we have talked about earlier, we can say that there is a strong positive relationship between age and weight. And it means that as the age increases, the weight also increases. Correlation coefficient is a mean-based estimate and hence markedly influenced by extreme values, and thus does not provide a good description of the relationship between two variables when the distributions are skewed or when the data contains outliers. In our previous sessions, we learned that when there are outliers or extreme values, and when the data is not normally distributed, rank is an alternative method to use. Similarly, the same concept applies here. When the data has extreme values, we can rank the observations and calculate the correlation on the ranks to obtain non-parametric correlation. This non-parametric correlation is called Spearman's row correlation. Spearman's rank correlation coefficient could be computed for the cases where both variables are quantitative or when variables are quantitative and ordinal, or when we have one variable that's quantitative and another one that is quantitative ordinal. After studying the relationships about two variables, researchers often want to be able to make predictions on the value of one characteristic from the knowledge of another. The statistical method that allows us to study relationships and also enable us to make predictions is called regression. The whole concept of linear regression is about to draw the best fit straight line described by the correlation of the two variables. The least squares method is a way to determine the equation of the line that provides a good fit to the points. Squares method assures that the vertical distances from the data points to the best fit line is as small as possible. As the name shows, least square method minimizes the sum of squared residuals. Residuals is a very commonly used term in regression. They are the vertical distances between data points and the corresponding predicted values. One important thing to note here is that for least squares regression, the residuals have a mean of 0. The best fit line that's used for regression has a mathematical equation with the slope and intercept. This equation has a form of y equal to bx plus a, where x is the independent variable, or what we call predictor in regression, and y is the dependent variable. The slope of the line is b in this equation, and a is the intercept. Slope is the rate of increase or decrease of the dependent variable for each unit increase in the independent variable. For example, a slope of 2 means that every 1 unit change in x yields a 2 unit change in y. The y-intercept is the value of the dependent variable when the independent variable is 0. It's simply the value at which the fitted line crosses the y-axis. And in this slide, I've also presented the mathematical equations as to how we would calculate b, which is the slope, and a, which is the y-intercept. I have presented the regression equation using the data that we used for the illustration of correlation coefficients. I used the same data from those 5 individuals with age and weight to see if we would be able to assess the relationship between age and weight and also be able to make predictions. Based on the formula that was presented for the regression equation in the previous slides, I manually calculated the regression equation, and also I used this data in SAS and presented the regression estimates from SAS. As you see, the beauty of regression is that it would tell you the relationship between the variables, and it would also allow you to make predictions for any values of the dependent variable using the equation. So according to the calculation, you see that our regression equation is 2.47 times x, any value of x, plus 58.94. So it means that I could plug in any value of age that I want and be able to predict what the weight for that specific X would be. Multiple regression is an extension of simple linear regression. It's used when we want to predict value of a variable based on the value of two or more other variables. So in the example that we were looking at the relationship between age and weight, but multiple regression would allow us to assess the relationship between age and weight or height or BMI or any other predictor variables that we want to look at. This was the discussion for this week. As you work on your analysis journal, please let me know if you have any questions. You can email me or you can post it on Ask the Prof, and I'll be able to assist you with that. Thank you.